It's the late 90s. With titles like Doom and Quake, id Software has changed gaming forever. Online multiplayer first-person shooters are becoming more and more popular. id Software has a radical idea. What if we dropped the single-player campaign entirely? What if the next game was only an arena shooter? But to justify their decision, the multiplayer had to be flawless. It had to run on low-spec machines and dial-up connection, while at the same time pushing graphics, physics, and gameplay to new levels. They wanted to create a fast-paced arena shooter that felt smooth on the average PC. So, they had to beat the limitations of bandwidth, latency, and reliability. Instead of waiting for the technology to improve, they decided to challenge it, pushing the limits of what's possible. What they built became the foundation of modern multiplayer networking, pioneering ideas and concepts that are still used today. It's not about frameworks or third-party libraries, it's the evolution of the engine architecture they had been shaping since Doom. Refined game after game. And that's why every computer science student or even experienced developer should study it. It's a masterclass in fundamentals. In my opinion, it deserves a place in every CS curriculum. In this video, I'm gonna talk about the snapshot system, delta compression, Huffman compression, client-side prediction, and why they used UDP instead of TCP. This is the Quake 3 netcode. Okay, so first let's start with the problems. This sounds like a description of a dinner with my family. Anyways, at that time it was facing what I call the impossible triangle: bandwidth, latency, and reliability. Bandwidth was low. Keep in mind most people were still on dial-up. If you're younger, you probably never heard a dial-up modem. It made this kind of alien sound and somehow we all just accepted it as normal. But if you think about it, nothing ever since has sounded like that. And also your phone didn't work. Okay, so bandwidth was limited. So they couldn't just push every little game change across the connection. Then the latency was high. If the client waited for the server to confirm every move, the game would just feel unresponsive. And then there was reliability. You had to accept the fact that packets were going to get lost. That's just how networks operate. And of course, for the guy having a full crash out, yes, sweetie, you could use raw dog TCP to guarantee delivery. But TCP comes with a lot of overhead. It resends old packets even if the information is no longer relevant. And in a shooter, if something happened 5 seconds ago, there's no point in retransmitting it, most of the time. This of course doesn't include all messages, everything, but most gameplay packets are not worth resending, so they decided to go with UDP. I'm gonna talk about this in detail. Okay, now the most impactful high-level decision in the game design was this. Quake 3 had no single-player campaign, so the multiplayer had to carry the whole game. It had to work. And you know why? Because it wasn't 2025 where everyone ships half-ass finished games for the full price. For like $80 and then you gotta buy the DLC and then the premium pack to have 2 more missions. I think we're just collectively accepting too much and gradually lowering our standards. But how do you solve something like this triangle here? The answer is you don't solve it with one big magic trick. In fact, it is very rare that you solve all bottlenecks with one decision. Usually, you come up with a lot of small ideas, each one covering one limitation. And then when you stack them all together, you can push through this plateau. Now, to easier understand how they put all of this together, let's start with the Quake 3 client-server architecture and the snapshot system on a very high level. Okay, so if you watched my last Quake video, you know that the game is split into 2 parts. The client and the server. The client renders the game, does a bunch of other stuff, handles your input, and then sends that input to the server. Now the server holds the authoritative game state. It holds the true state of the game. Since, after all the players want to play the same session, the same game. So the server receives all inputs from all clients, updates the game state, and sends the updated game state to all the clients. That's the model. Pretty simple on paper, but making it actually work for a fast-paced FPS is a whole other story. Stay with me now. Under the hood, the server runs a snapshot system. In regular time intervals, the server creates a snapshot of the current game state containing all new updates from the clients. Think of a snapshot like as a photograph of the whole game state at a specific moment in time. It contains all the relevant information. Now they can just take the snapshot and send it to all clients, right? Yeah, they could if there wasn't our triangle of limitations: bandwidth, latency, and reliability. So let's address the most important concepts that made this work. Okay, if you're dealing with low bandwidth, your only option is to send less data. So first ask yourself, do I really need to send all of this data all the time? That's also something you should ask yourself when sending the 11th reel today to someone who hasn't even reacted to the previous 36. Anyway, ask yourself, do I need to send the whole snapshot? I mean, you can, but in reality, not everything is changing all the time. So why not just send the delta, the difference between the last two states? So in case nothing has changed for an entity, you just send one bit that indicates nothing has changed for this entity. That's delta compression. But how are we gonna tackle the problem if one client gets out of sync and the other one is still in sync, not to be confused with n-sync? You can't send the same delta to both, since you would lose information. So for each client, the server keeps a snapshot buffer that holds the last 32 snapshots for that client, a history. So the server creates a delta for each client based upon the last snapshot that has been acknowledged by the client. In case you're wondering, but isn't that a lot more processing on the server side than sending out everything all the time? Yes. And this is a trade-off. But our bottleneck isn't the server-side processing power. The bottleneck is the bandwidth. But let's continue. So when you reduce the full snapshot to just the delta, you have scoped out the information that has to be communicated to the clients. Now, what you can do is you can try to represent the data, the same data, but with fewer bits. And that's where the Huffman compression comes in. Don't worry, I'm going to talk about this in detail during the video. Okay, and then we have latency. When talking about latency, you can of course wait every time for the server to approve, acknowledge your action. But what you can also do is act now and reconcile later in case your action is not valid. That is client-side prediction, and it makes the game feel more responsive or super responsive because you're not waiting for the other side to acknowledge your actions. And for the reliability, Quake 3 chose UDP over TCP. UDP is lightweight and fast, and if a packet gets lost, the game just keeps going. I mean, it's better to miss a frame than freeze for 2 seconds while waiting for all data. For specific actions, they have built in reliability into the UDP frame. For example, for actions like a client leaving the game or changing the map. Now, if you put all of that together, snapshots, deltas, compression, prediction, UDP, you get the core of the Quake 3 netcode. Not one giant breakthrough, even though many of these ideas are genius in my opinion, but as you can see, it's a bunch of smart decisions working in harmony. Now I'm gonna go through each of these concepts in more detail. So first we're gonna talk about the techniques that minimize the needed bandwidth. Since Quake is a FPS game and not chess, you can't see everything all the time, which, when you think about it, is actually great news for your bandwidth. So the first thing you do is ask yourself, why would you even try to send data about the stuff the player can't even see? And this is where the potentially visible set or PVS comes in. When the map gets compiled, they do some pre-processing and figure out from every possible position in the map what areas you could potentially see. So if your map looks like this, you get information like if you're in sector A, you can potentially see sectors B and C, depending on your orientation, of course. but you will definitely not be able to see D, E, and F. All of this information gets cooked into the map, so at runtime, we don't have to do any expensive line-of-sight calculations. Let's take a look at the server snapshot code. So we go in code, server snapshot.c. We have this function called server add entities visible from point, so it basically loops through all the entities in the world. But before adding the entity to the PVS pool, it starts by doing all these, let's call them knockout criteria checks. So, for example, if an entity is not active, there is no point in checking where it is. It doesn't make sense doing first the PVS calculation and then checking if it's active. And this is how you should design your code. I know it sounds like common sense, but it isn't that common sense in practice. So the goal is to filter out everything before you go into expensive calculations. Or even if the calculation per se isn't expensive, why would you do it if you can just drop it entirely? Okay, so it starts by defining a bunch of stuff, and this here is the main loop. So it's basically iterating through every single entity starting at 0 and then going all the way up. And then we have this cascade of knockout criteria, filtering, or whatever you want to call it, which I mentioned. So all of these are just bit checks or integer comparisons, so it's very cheap. And here we have the PVS check or PVS lookup. This is a chain of bitwise operations that basically checks if the entity's cluster is visible from the client's position. Now, what is a cluster? A cluster is a group of nearby map areas that tend to see the same stuff. So instead of tracking thousands of tiny small individual spaces, Quake tree bundles them together. So the whole system is way more efficient by doing it this way. I mean, I could make an own video about only talking about clusters and PVS, but let's continue. Okay, so this client PVS is the pre-computed bit array where each bit represents whether a specific cluster can be seen. So this loop is just asking, can I see any of the clusters this entity belongs to? And as soon as it finds one visible cluster, it breaks out and it adds the entity. This isn't doing complex 3D ray tracing or anything crazy, it's just looking up in that pre-computed table that I mentioned. So by doing it this way, the question, can the client in area A see an entity in cluster D becomes just, is the bit for cluster D set in the pre-computed visibility array? And boom, table lookup done. Okay, so this cluster nums lets you draw the conclusion that entities can span across multiple clusters. So the loop just checks if any cluster the entity touches is visible. And as soon as it finds one visible cluster, it breaks out and adds the entity. And at the end of this function, we have this really cool portal feature. So if the entity is a portal, it recursively calls the same function from the portal's destination, adding basically everything visible through the portal. So, for example, mirrors or teleporters automatically show what's on the other side, okay? So after this PVS step, instead of having to deal with hundreds of entities, you might only have 20 that the client actually needs to know about. And that's saving enormous amounts of bandwidth. Okay, that's that about the potentially visible set. Now let's look at the delta compression, because the code is surprisingly elegant once you understand what's happening. So let's first take a look at the entity state struct, which is located in code, game, shared header file. The entity state struct holds data basically for everything. And I'm talking about all the data for all the objects in the game, for the players, rockets, items, everything. Now, the classic object-oriented programming class way to handle this would be to write custom code for each field. Like, just bomb up everything with getter and setter functions and then build in a chain of impossible inheritance. I don't know why, but these university classes love inheritance more than, I don't know, frat boys. So you would end up like having a gazillion functions to get and set data and then do that for each entity type. Something like if position changed, send position. If health changed, send health. And you would end up with such an enormous amount of code that's also very inefficient. And it's also inefficient in a maintenance sense, because imagine you want to add something and then you also need to add code to compare it, to encode it, decode it, and all that stuff. It's very error prone. But the IT guys did something way more elegant. So let's first start with the net field. And this will all make sense when we come to the write delta entity function. If you're not a prompt engineer, of course. So let's open message.c, and here we can find the net field struct. This is the struct for each entry in the lookup table that drives this whole delta system. It's got the field name, the byte offset within the struct, and the number of bits to use for network encoding. And then comes a little bit of preprocessor magic that makes the table easy to maintain, but don't get scared. I know when you first time see something like this, it looks like, do I really need a job? But let me break it down so we can understand what's actually happening in here. Okay, let's go step by step. So the first part is hash x. That hash symbol is the stringification operator. It just takes whatever you pass in and turns it into a string. So if you write netf position, for example, that hash x becomes a string holding position. Simple enough, it's just the field name as a string. Okay. The second part is where it gets scary if you're a Python developer. This is calculating the byte offset of a field within the struct. Now, let me walk you through this step by step because there's a really clever trick happening here. Okay, so first let's take a look at this. This is a cast. What this does is it takes the number 0, which is the null pointer, and casts it to a pointer to an entity state struct. So we are pretending that there's an entity state struct sitting at memory address 0. Obviously, there isn't really a struct there, but the compiler doesn't know at this point. Okay. Next, we have this x. This accesses the field we are interested in. So if we call netf position, this becomes position. We are accessing the position field of this imaginary struct at address 0. And then comes the AND operator. This takes the address of that field. Now, here's the clever part. If our struct starts at address 0, and we take the address of a field inside it, that address is the offset of the field from the beginning of the struct. If the position field is 12 bytes into the struct, its address when the struct is at address 0 is then 12. Okay, does this make sense? Probably not, but it's a very elegant way, and you will see why this is important. And finally, we cast this whole thing to an integer. So we get a nice integer offset value. Okay, so the compiler is doing all this math at compile time to figure out where each field lives within the struct. And this becomes really powerful, and you will see it. Okay, right below that, you see the actual table with the entity state fields. And this is where we use this netf. Okay. I mean, look how clean this looks like, even though you can't probably understand what's happening here. It looks really nice. So each line is just a field name and wrapped in this netf, followed by the number of bits to use for encoding. And the compiler now processes each of these netf macros and calculates where that field actually lives in the entity state struct. So each entry ends up with three things: the field name, the byte offset from the start of the struct, and the number of bits to use for encoding that field over the network. If you're wondering now what's this last bit for, that last bit just tells the network code how much precision to use when sending this value. Okay, so if you scroll up, you will see that value of 0 means it's a float and should be encoded accordingly. While other values, for example, like 32, specify how many bits to use for these integers. Okay, for, I don't know, timestamps or something. Now, you may be thinking, or maybe not, but Tariq, couldn't we just hard code these offsets? Why do we need this sorcery? And that's actually a really great question, because the answer reveals why this approach is genius. Yeah, I mean, you probably wouldn't come up with this approach to solve this type of issue. And that's why it's very important to study these code bases, because this isn't something a university teacher would necessarily teach you in his programming class. I mean, sure, you could write something like, I don't know, just hard code all the offsets and that works fine until you need to change the struct. And you're going to have to change the struct a lot. I mean, game development is very iterative. You're constantly adding new fields, removing old ones, reordering things for performance, or changing data types or something. And let's say you added a new field on top of this entity state. Now, for every single offset in your hard-coded table, you would need to make a change. And for example, health isn't anymore at offset 48 and 52 offset is wrong for the weapons. Position moved, angles moved, everything shifted. So now you have to manually go through your entire table and recalculate every offset by hand. I mean, you could of course script this part. By doing it with this approach, you just recompile and it automatically recalculates all the offsets for you. The compiler knows the struct layout, so it figures out where everything is. You add a field to the struct, you add one line to the table using the netf, and you're done. No manual offset calculation, so no chance of getting anything wrong. Now, besides that, we have another advantage when it comes to struct padding and alignment. As you know, sometimes the compiler adds invisible padding bytes between two fields to align them properly for performance. So you might think two integer fields are 8 bytes apart, but the compiler added 4 bytes of padding for whatever reason. So now they're actually 12 bytes apart. But with this approach, you don't have to think about any of this. The compiler just calculates it and you get the offset. Okay? And there's of course the thing with the portability. I mean, different compilers on different platforms might lay out the structs differently. They might use different padding rules or different alignment requirements. And with hard-coded offsets, your table would be wrong on some platforms. So this isn't about something you couldn't do otherwise. It's more about this not having to be tedious and not having to do this error-prone manual work every single time you change something, because you put the responsibility on the compiler to do this, let's call it maintenance stuff. Okay, now let's see how this table actually gets used. If you scroll down now further in the message.c file, you'll see this message write delta entity function. This is where it gets interesting. So this function takes two entity states, the old one and the new one, and then figures out what has changed. It starts by defining a bunch of stuff, and then we get to this loop. So this function has two very important loops. And the first one goes through the fields and looks for the last changed field. That's this LC here. Why is this important? Well, imagine you have a series of fields 100, 100, and then a lot of zeros. Now, every bit is a field. 1 means we have a change, and 0 means we have no changes. Now, this LC variable marks the spot, so to say, where the last change is located in the entity fields. And it tells the rest of the function then, okay, here is where the last changed field is, and after that, everything is unchanged. So you can cut this tail off. Drop the tail like a lizard. Okay, and then we have these checks. If nothing has changed, you can return immediately. There's no point in comparing fields if there are no changes. But if there are changes, then comes the second loop. And in this loop, we go through all the fields and compare all the values, and we write the delta bits. Okay? And generally speaking, the loop doesn't really know what it's comparing. And that's elegant about it. Okay, so the delta compression really scopes out only the information that really needs to be sent. In practice, it looks something like this. Let's say we have a player entity that moves slightly and changed weapons. The old state position is 100, 250, weapon is 2, animation frame is 15. The new state position is 105, 250, weapon is 3, and the animation frame is still 15. Now, the delta compression sees that only the X position and the changed weapon, so it only sends these two fields. And now that's maybe 16 bits instead of hundreds of bits for the full entity state it would take. But we are still not done with the bit squeezing. So if you think about it, the PVS filtering and the delta compression scope out the data that we definitely need to send in the next game state update. And since we can't filter out any more unnecessary information, the only thing that we can do is to try to represent these update bits with fewer bits. And that's where Huffman Compression comes in. So after that's done, we have the stream of bits that we want to send in the next game update. So we run it through the Huffman Compression. Now let me explain how the Huffman Compression actually works. We're gonna start with a small example, and then I'm gonna take a look at the code. So Huffman Compression is basically like creating a key map for your data. Instead of every byte taking exactly 8 bits, we represent the most common byte values with just 1 or 2 bits. While very rare values can take up more than 8 bits. But since the rare stuff is, well, not being sent out that frequently, you end up saving tons of data overall. So what they've done is they analyzed the traffic during normal gameplay and found out that specific values are sent more frequently than others. They analyzed the byte frequencies. And then you get something like this, for example. 0, which basically means no change, appears 40% of the time, because most things don't change most of the time. Then 1, representing tiny movement deltas, appear 25% of the time. A 2, for example, like a slightly bigger movement, shows up 20% of the time, and very big movements, like teleporting, appear only 15% of the time. These are of course not the actual values from Quake, I'm just giving you an example. Now, in case you're wondering, how do you determine which value gets which key and how do you avoid ambiguity? Well, it's kinda simple. In our imaginary example, we have these 4 separate nodes: 0, 1, 2, and FF. Now, here's where the Huffman algorithm comes in. The rule is very simple. Always merge the 2 nodes with the lowest frequencies. So first we're gonna take FF at 15% and the 2 at 20% and combine them. Next we're gonna take the 1 at 25% and our new node at 35%, which we created in the step before, and combine these two. And now in the final merge, we combine 0 and the node 2 to create the full tree. Okay, now we assign the codes by following edge labels. Left edges are 0, right edges are 1. So first let's start with 0. So we go left, left is 0, and we end up in the leaf. So 0 is 0. Now we want the 1, so we go right, which is 1, and then left, which is 0, and end up in the leaf. 1, 0. FF, we're gonna go right, right, left, which is 1, 1, 0. And then for the 2, we go right, right, right. 1, 1, 1. And here's the beautiful part about why this works without any ambiguity. Let's try to decode the bit stream 0, 1, 0, 1, 1, 0, 1, 1, 1. Okay, we start at the root. We read the 0, we go left, end up in the leaf, and then we reset to the root. We read the 1, we go right, internal node, that means we continue. We read a 0, we go left, and we end up in the leaf. Again, reset to the root. Now we read a 1, go right, then again 1, go right, and then read 0, go left, we end up in the leaf, and we reset to the root again. Now we continue doing this until we decoded the whole bit stream. And the result is a perfectly decoded bit stream with zero ambiguity. Now to demonstrate how much compression can we achieve with this Huffman compression, for example, if we send 5 bytes, these 5 bytes, without Huffman, that's 40 bits. With Huffman, it's only 11 bits. So we end up saving over 70% of data. Now let's take a look how Quake 3 actually implements this. So Quake 3 uses 2 different approaches, an adaptive Huffman and a pre-computed Huffman. It uses the adaptive for the initial connection handshake. It is located in the huffman.c file. So for adaptive, it uses this huff compress function. They used pre-computed Huffman trees for regular gameplay packets. Let's open code qcommon message.c. Now in message.c we have this pre-computed frequency table called message h Huffman data. So when starting the game you call message init Huffman, and that builds a Huffman tree from this frequency table. But how did they use this in the code? Well, when the game reads or writes bits in the message functions, it routes the data through the Huffman encoder, if compression is enabled, of course. Since the client and the server use the same Huffman tree, there is no discrepancy when the payload needs to be coded or decoded. All of this works because game network data has a very predictable pattern. You have always a lots of zeros from delta compression and you have small integers for coordinates. So certain values appear way more often than others. I mean, if the frequencies were all the same, if you have like a even distribution of the values, it wouldn't make sense integrating the Huffman compression in all of this. Okay, so that means they integrated this Huffman compression directly in the read bits and write bits functions. Now, generally speaking, the compression pipeline is highly efficient. PVS cuts out maybe 80% of the data you don't need, delta compression reduces what's left from hundreds of bits per entity down to maybe 20 or 30 bits on average. And then Huffman squeezes that remaining data by another 50 or 70% by exploiting the patterns in game data. You end up taking what should have been multiple megabytes per second and turning it into a few kilobytes per second. And the crazy part is, this isn't just clever compression, it's compression that's specifically designed around the patterns that actually exist in real game data. They didn't just apply generic compression algorithms, they built compression that understands what Quake 3 network traffic actually looks like. And that's why you got that much compression. Alright, so we've solved the bandwidth problem, but now we had the second fundamental constraint, latency. And this one's a real mind bender because the solution involves something that sounds a bit counterintuitive, letting every player live in their own personal timeline from a first-person perspective. Now, before we continue, a word from our today's sponsor, Brilliant. Instead of refreshing your inbox for the daily job rejection email, since apparently nobody's hiring anymore, just get Brilliant. It's got interactive courses on math, data analysis, and computer science that actually make your brain feel good. I use it when I need to recover from making spaghetti, and not the Italian one, or when I want to sound clever around friends who still think I fix printers for a living. The best part is you can start from zero. Brilliant takes you from the basics and builds up step by step, even if your attention span has been reduced to the length of my last relationship. It's basically an arm workout for the brain. To learn for free on Brilliant, go to brilliant.org/Tariq10x, scan the QR code on screen, or click on the link in the description. Brilliant's also given my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Now, back to the video. Okay, now the problem with latency is when you press a key, the signal has to travel to the server has to process it and send back the result, and only then you can see your character move. That's what we call a full round trip. And on the internet from the 90s, we're talking about delays that make the game feel like you're controlling your character via screen sharing. There is just no way to speed it up with elegant software tricks to lower the latency. If a train has a top speed of 50 miles per hour, it doesn't matter how light the freight is that the train is carrying. It can't go any faster. So they had to accept that as a hard limitation and create something that will give you the illusion that the game is super responsive. Now, their solution breaks down into two core mechanisms that attack different aspects of the latency problem. First, we have client-side prediction, which makes your character feel instantly responsive by running the game physics locally. Second, we have interpolation and extrapolation, which make other players look smooth despite receiving choppy updates from the server. Together, these two create the illusion that latency doesn't exist. Now, I have talked in another video about the client-side prediction, and I have to mention that Quake wasn't the first game that implemented it. Ken Silverman was actually the first one to implement it, the creator of the build engine which powered Duke Nukem 3D. He implemented client-side prediction in January 96, 7 months before John Carmack added it to the Quake world in August 96. You can also find it in the Duke Nukem source code. And I might be making few more Duke videos in the future. In my opinion, it's genius, even though it looks like a very normal concept nowadays. Okay, so the core idea is very simple. When you press a movement key, instead of sending that input to the server and waiting for permission to move, your client immediately runs the exact same movement physics that the server uses. So you see yourself move instantly, even though the server hasn't even received your input yet. Now let's take a look at the code. If you open code, cgame, cgpredict, there is a function called cgPredictPlayerState that runs every single frame. This is the heart of the prediction system. I'm gonna walk through this, but on a very high level. As you can see, there are many comments in this part of the code that's usually a good indicator that a section is more complicated than the rest. In good projects, of course. Bad projects are full of useless comments. Okay, so the client needs to figure out which commands it needs to execute, what to predict. Every time you press a key or move your mouse, the client creates a command, a little packet of data that says at this moment in time the player wanted to move forward or turn left or whatever. The server sends back snapshots that tell you I've processed everything up to command number, let's say 9. So when the predict system runs, it looks at the acknowledgement and says, okay, the last thing that the server confirmed was command number 9, but I'm currently at command 14 because I've sent 5 more commands since then. So I need to replay commands 10, 11, 12, 13, and 14 to figure out where I should be right now, okay? I'm not gonna dig deep into every line here, so I'm obviously skipping some parts. And then at some point we arrive at this loop. This loop is walking through all those unacknowledged commands one by one. And for each command, it calls the trap function. In my last Quake video, I talked about trap functions, if you remember. Trap get user command to retrieve the command from the buffer. And then it calls pmove, that's the physics function. And here's the beautiful part. pmove is the exact same code that runs on the server side. And it's located in this pmove.c source file. So both client and server link to the same file. So when your client runs pmove with the command number, I don't know, 11, it gets the same exact result as the server got when it processed command number 11. The pmove function takes this pmove struct as an input, and this struct contains basically everything you need to run the physics. It contains the player state, the command to execute, and everything. And that's the essence why the prediction is so accurate. So it's not guessing, it's not a gamble. It's literally running the same physics simulation with the same input so it gets the same output. And then when the update arrives, the client just checks if it's been right, and if not, it starts a reconciliation routine to get back on track. Now, client-side prediction solves the problem for your own character. But what about everyone else? This is where interpolation and extrapolation come in. And this is solving a completely different aspect of the latency problem. So, for example, the server is sending you snapshots at maybe 20 frames per second, but your game is running at 50 frames per second. If you just displayed each snapshot exactly when it arrived, other players would be like teleporting around. And that's 100% valid reason to smash your keyboard. I mean, the client doesn't display the latest snapshot immediately. Instead, it deliberately runs about 100 milliseconds behind, which gives it 2 snapshots to work with. And then it smoothly interpolates between them. You can see in code cgame cg ends.c, we have this function interpolate entity position. Okay, so this function is pretty straightforward. It takes 2 snapshots, the current one and the next one, and blends between them. The function uses this pre-calculated interpolation factor f, which is basically a number between 0 and 1 that tells you how far along you are between the 2 snapshots. Meaning if it's 0, you're exactly at the first snapshot, and if it's 1, you're at the second snapshot. If it's 0.5, you're halfway between them. Now, here's how it works. First, it evaluates where the entity should be in both snapshots with this BG evaluate trajectory. This takes the trajectory data from each snapshot, which includes position, velocity, and movement type, and calculates the exact position at that moment in time. This handles things like entities that are accelerating or following curved paths. Then it does a simple linear interpolation between those two positions using that interpolation factor f that I mentioned. And then it does the same exact thing for the angles. So basically same idea, evaluate the angle trajectory for both snapshots and then interpolate between them using the same interpolation factor. So the client is constantly sliding entities from where they were to where they're going, and creating this illusion of continuous movement even though it's only receiving 20 updates per second. So what's brilliant about this whole system is how it creates this illusion of instant responsiveness. Smooth gameplay despite the fundamental constraint of latency. You get instant response for your own actions through the client-side prediction, and you get smooth visuals because of interpolation and extrapolation. And the price you pay is that everyone is living in a slightly different timeline. I mean, most people never even notice that it works like this, okay? Alright, so we've conquered bandwidth and we've beaten latency, but there is still one more fundamental problem with the internet from the 90s, reliability. And this is where Quake 3 made perhaps its most counterintuitive decision. They decided to embrace packet loss instead of fighting it. Now, when most people think about network reliability, they think about TCP, the protocol that guarantees every byte will arrive in the correct order, no matter what. TCP is like a perfectionist postal service that will keep redelivering the same letter until you confirm you got it. And it won't deliver letter number 2 until letter number 1 is safely in your hands. For most applications, this is exactly what you want. But for a real-time game, this perfectionist approach is actually suboptimal. See, the thing about game data is that it has an expiration date. If a packet containing last frame's player positions gets delayed by half a second while TCP tries to retransmit some earlier packet, that data isn't just late, it's actively harmful. You don't want to know where players were half a second ago, you want to know closely as possibly where they are right now. So Quake 3 made a radical choice. They threw out TCP entirely and built their reliability on top of UDP. UDP is like a much more relaxed mail service that just throws packets at their destination and hopes for the best. If a packet gets lost, well, maybe the next one will make it through. Now, if you're looking for reliability logic in the network transmission code, you're not going to find it there. Let's open the netchannel code and look at the netchan transmit function. Okay, this write long takes the message and it adds a sequence number so you can detect packet loss, and then this net send packet sends it over UDP and moves on. So where's the reliability? Well, it's built in at a higher level in the message system, and both client and server have their own implementation of it. So on the server side, if you look at the code server main.c, there's a function called add server command. This is where messages that absolutely must arrive get stored, like player joined, map changed, or I don't know, server settings updated. These commands must go into the reliable queue. So the server keeps these commands in a circular buffer and resends them with every outgoing packet until the client acknowledges them. On the client side, it works the same way, but in reverse. If you look at the code in code client cl main.c, there's this add reliable command. So this handles reliable messages from client to server. Things like changing your nickname, sending chat messages, or requesting map downloads. So we have the same circular buffer pattern, same logic. Both sides keep resending their reliable commands until the other side says, okay, I've received it. But here's where it gets really interesting. How do you make a system work when most of your data is being sent unreliably? The answer is one of the most elegant pieces of engineering in the entire Quake 3 codebase. It's the circular snapshot buffer. I mean, the idea is brilliant in its simplicity. Instead of trying to make sure every packet arrives, they designed a system where losing packets doesn't have a major impact. Both the server and the client keep just a rolling window of the last 32 snapshots they dealt with. So when the server wants to send you a new snapshot, it doesn't just delta against the previous one. It can delta against any snapshot in your 32 slot window that it knows you received. Let me show you how this works. So in the code, if we open the server snapshot.c file, there's this write snapshot to client. This is where the server decides which snapshot to use as the base for the delta compression. The server tracks which snapshot the client last acknowledged in client delta message. So if the client says, I got snapshot 27, but snapshots 28, 29, 30 got lost, the server just delta snapshot 31 against snapshot 27. In a traditional system, this would be a disaster. You'd either have to retransmit all the missing packets or send a huge full update. But with this Quake system, missing packets in between don't really matter that much. And the circular buffer is using this binary matrix, so no complex buffer management is needed. On the client side, we have code client parse.c. We have this client parse snapshot function. The server tells the client which snapshot to use as the base. The client looks it up in its own circular buffer, applies the delta, and reconstructs the current state. If you have any missing snapshots in between, it doesn't really matter. So the end result is a system that's incredibly robust against network problems. It's a system that handles problems gracefully instead of failing catastrophically. So by designing around these actual requirements, instead of trying to force a traditional reliability model, Quake 3 created a network system that's both more robust and more efficient than anything based on TCP could ever be. And that's how they solved their reliability problem. It's the same kind of paradigm shift we saw with the bandwidth and the latency. Instead of fighting the constraints, they embraced them and designed around them. Conclusion. You know, I'm sitting here looking at all this code and I'm thinking how wild this whole story really is. Like, imagine everyone's telling you that what you want to do just can't work. The internet is too slow, too unreliable, and too broken for real-time gaming. And honestly, they weren't wrong. I mean, the numbers were pretty brutal. But instead of giving up, these guys did something that still makes me smile when I think about it. It's just like having a drink with the boys and saying, hell yeah, let's do this. I mean, they looked at every single limitation and basically said, okay, what if we design around this instead of fighting it? What if we don't care about packet loss? What if we don't try to keep everyone perfectly synchronized all the time? What if we just embrace the chaos? And that's exactly what they did. Every technique we just walked through, the delta compression, the client prediction, Huffman, none of it came from having better hardware or faster connections. It all came from being clever about working with what they had. They turned their constraints into their competitive advantage. Innovation always comes from limitations. And the crazy part is how well it worked. I mean, we're still using these exact same ideas today. When you're playing Call of Duty or whatever game came out for $80 this month, you're experiencing the direct descendants of these techniques. 25 years later, and nobody's really come up with anything fundamentally better. And that's how you know something is truly revolutionary. When it doesn't just solve the immediate problem, but it becomes the foundation that everyone else builds on. The best solutions often come from the worst situations. When everything's working against you, when you have no choice but to think completely differently. Some of the most elegant code I've ever seen came from developers who had their backs against the wall and had to be creative. Anyone working in embedded knows this. It's easy to develop when your software has to run on 16 gigs of RAM, but how about I give you 4 megabytes and I also want you to do a flash over the air with a A-B swap. It makes you wonder, what problems are we just accepting today because they seem too hard or too fundamental to change? What assumptions are we making that maybe we shouldn't be? Because if there's one thing this story teaches us, is that sometimes the impossible is just waiting for someone brave enough to ignore what everyone else says can't be done. And I'm not trying to give you a motivational speech how everything is possible, because we as humanity clearly can't even manufacture printers that work when we need them. Okay, now I want to take the moment and say a big thank you to my Patreons and YouTube members. Your support over the past year really helped me. Your memberships, messages, emails, everything. As you know, I'm continuously upgrading my setup, trying to improve the format, experimenting, content-wise, trying out new ideas, and also listening to your constructive criticism. Your comments and suggestions really help me to create better and better content. If you want to support the channel, there's a Patreon link in the description, or you can become a YouTube member, or just leave me a comment. So, that's it for today. If you like the content, hit like and subscribe, and see you in the next one. Tariq 10X.